Hi, and welcome to part 2 of this tutorial on C# exception handling. In part 1, we looked at a general overview of C# exception handling. In this part, we'll start to build a basic application. I've chosen a basic calculator as the theme of this tutorial, deliberately because I want to keep the code example as simple as possible so that the exception handling aspect of the tutorial stands out. So let's start by creating a new project in Visual Studio 2019. I'm using the Community Edition. It's a free code editor that you are able to download and install. You can use whichever suitable code editor you like to follow along with this tutorial. However, if you'd like to install Visual Studio 2019 Community Edition, I've included a link below in the description to a video that can guide you through the installation process. So let's continue with the project creation process. Let's select the console app.NET Core project template, and let's name this project Basic Calculator. Let's start by writing code to output a heading to the console screen. Let's output the text Basic Calculator as the heading for this application. Okay, let's call the console.writeLine method without passing an argument to it, in order to add an empty line below the heading code we have just written. The next step is to write code that prompts the user for the first operand value. So let's use the console.writeLine method to output text to prompt the user to input an integer value for the first operand. Let's declare two local integer variables named operand1 and operand2 at the top of the main method. Let's also declare an integer named result, which will store the result of the operation performed against the values stored in the integer variables we have just defined, namely operand1 and operand2. Let's use the int.parse method to convert the user input, which will be captured as a string by the console.readLine method, to convert the inputted string value to an integer value. This calculator is a very basic calculator and will only accept integer values for operand input values. So the code to capture the user's input for the second operand is similar to the code we have just implemented for the first operand, so let's copy the code used to facilitate the capture of the first operand and paste it below this code. Then we can simply change the parts of code that are specific to the capture of the second operand. Let's write the code to prompt the user to input the operator symbol that is representative of the type of operation the user wishes to perform on the relevant inputted operands. The prompt text should inform the user that this basic calculator is limited to the following operations, namely plus, minus, multiply, and divide. So in order for the user's input to be valid, only one of the four symbols representative of either a plus, minus, multiply, or divide operation should be entered for the operator symbol input field. Let's define a local variable at the top of the main method as the char date type, and let's name this variable operator symbol. We know that the console.readLine method captures the user's input as a string data type. An operator symbol only needs to be one character in length, which means we should use a variable defined as the char date type to store the user's input for the operator symbol field. This means that we must convert the user's input for the operator symbol from the string value captured by the console.read method to the char date type before we assign the newly converted value to the variable we have just defined as the char date type, namely the operator symbol variable. We can convert the string value captured by the console.readLine method through the use of the C# built-in char.parse method. So let's write a switch statement to compare the user's input for the operator symbol against the basic mathematical operators supported in our basic calculator application. So the match expression is the operator symbol inputted by the user. The first match pattern is the plus operator symbol. The second match pattern is the minus operator symbol. The third match pattern is the asterisk symbol, which is representative of the multiplication operator in C#. And lastly, the fourth match pattern is the / symbol, which in C# is representative of the divide operator. Each match pattern is evaluated from top to bottom, and each switch section is mutually exclusive, meaning that, for example, if the user enters a minus symbol, the minus operation will be performed against the operands and none of the other operations will be performed. So one or none of the operations will be performed based on the user's input. And lastly, let's write code to output an interpolated string, which includes the mathematical expression and the result of the operation to the console screen. So there is a red squiggly line under the result variable, and this is because at the moment, the switch block is not handling a case where an invalid operator is inputted by the user, and the result integer variable has not yet been initialized with a value. Let's initialize the result variable with a value at the top of the main method, where the result variable is declared to 0 to get rid of the red squiggly line. We will handle the validation and exception handling for this application as the tutorial progresses. So in the interests of formatting, let's add an empty line between the user input related output and the output result. We can add this empty line through the use of the console.writeLine method, whereby no arguments are passed to the console.writeLine method. Okay, let's run the code and test our basic calculator application. So let's enter 200 as the first operand. Let's enter 200 as the second operand. Let's enter the plus operator symbol to indicate to the basic calculator application that we wish to perform an addition operation against the two integer operands we have inputted. And the calculation expression followed by the result is outputted to the console screen. So 200 plus 200 equals 400 is outputted to the screen, which is an expected result. So let's test a subtraction operation. Great. Let's test a multiplication operation. Great. And lastly, a division operation. Excellent. Okay, so as developers, we have control over certain aspects of our applications. For example, the look and feel of our applications and the logical flow of our applications. However, when it comes to user input entered into free text fields, we have limited control. As developers, we have two choices when handling user input. We can write code to validate the user's input, and if the user has entered invalid data for a particular field, we can prompt the user to try again, as well as provide feedback to the user as to the nature of the user's invalid input. So instead of allowing for an exception to be thrown, we can prompt the user to try again. Handling user input with appropriate validation is recommended rather than just throwing an exception. We could handle invalid user input by throwing an appropriate exception. We can then catch the exception through the implementation of a try-catch block. The user's input can trigger a built-in C# method, like for example, if the user left a field blank and therefore an empty string was passed to the int.pass method, a format exception would be thrown. We could handle this case by catching and handling the format exception by wrapping our code within a try-catch block. Later in this tutorial, we'll demonstrate a combination of both validating user input as well as exception handling. When a user inputs invalid data for any one of the relevant fields, the user will be given 5 chances to input correct data. On the 5th try, if the user's input is still invalid, an exception will be forced and then handled in code. For the moment, let's look at how we can handle an exception caused by the user's invalid input through the use of a try-catch block. Just to reiterate, it is always recommended that user input be appropriately validated in code rather than just throwing an exception or allowing an exception to be thrown. For the purpose of introducing the use of a try-catch block for exception handling, let's temporarily handle the user's invalid input by including the relevant code in a try-catch block. In the 5th part of this tutorial, we'll create validation code to handle the user's input, whereby if the user continues to enter invalid data on the user's 5th attempt, try-catch code will handle the exception caused by the user's invalid input. Using the Common Language Runtime's exception handling model is relatively resource intensive, so it should only be used when absolutely necessary. Before we implement try-catch code, let's run the code, and although it is more likely that a user will input a valid number, there is a possibility that the user could simply press the enter key without inputting a value. So let's do that and see how the application responds to this. And you can see that the code is failing at line 18. The code is stopped at this line and cannot continue running the subsequent lines of code because an exception has been thrown. The text format exception clearly indicates the nature of the exception. Brief descriptive text of the exception follows. As you can see, the text states, input string was not in a correct format. So what has happened here is that an empty string has been passed to the C# built-in int.parse method, and this method has thrown a particular type of exception, namely the format exception. So let's see what other exceptions we can cause in our application. Let's run the code. Let's enter alpha and numeric characters for the first operand field. And once again, an exception is thrown when the int.parse method is called to attempt to convert the user's input from a string to an integer. The exception is thrown because the string argument passed to the method is in a format that cannot be converted to an integer value. So let's run the code again. This time I'm going to enter a number with a value that falls outside of the supported range for an integer data type. So let's enter a fairly large number to force an exception. And when we press the enter key to confirm our input, you can see that code execution is immediately stopped at the line of code which is attempting to convert the user's input from a string value to an integer value. But this time the exception type is different. The unhandled exception type thrown here is an overflow exception. The error message states that the value inputted was either too large or too small for an int32. Okay, so we have just seen what happens when the user's input for one of the integer operands is a numeric value that falls outside the range of values supported for the integer data type. An overflow exception is thrown. What happens if the operands are valid integers, but the result of, say, a multiplication operation exceeds the maximum number supported for the integer data type? Let's run the code and enter two valid integer operands that are relatively large in value, but themselves will not cause an overflow exception to occur, and then choose the multiplication symbol for the operator so that the multiplication operation is performed on these two relatively large operand integer values. Okay, so no exception was thrown, but the result is a negative value, which doesn't seem to make mathematical sense. So the reason for this is that in C#, if an integer operation results in a value that falls outside the range of the values that an integer data type can handle, the operation proceeds anyway. So by default, the Common Language Runtime doesn't check for overflow exceptions when an integer mathematical operation is performed. Let's look at a basic example of what occurs at the binary level when an integer operation results in an overflow. So our operands are both defined as the byte data type. Note that the byte data type is an integer data type that supports values ranging between 0 and 255. So the first operand is assigned a value of 255. The second operand is assigned a value of 1. When the second operand is added to the first operand, the result is 0, which doesn't make mathematical sense. The answer, of course, should be 256. 256 exceeds the range of values supported for the byte data type. So if an overflow check had been done, an overflow exception would have been thrown, but instead the operation proceeds anyway. To understand what is happening, let's look at our values at the binary level. The first operand is a value of 255, which is represented in binary like this. The second operand is a value of 1, which is represented in binary like this. So when the second operand is added to the first operand, instead of overflowing, because 256 in binary requires 9 bits for its representation and the byte data type is limited to 8 bits of data, the result cycles like an odometer. So, for our basic calculator application, we want overflow checks to occur so that an exception will be thrown if an integer operation occurs that results in a value that does not fall within the range supported by the integer data type. The C# language allows us to force the CLR to perform the overflow checks by appropriately applying the checked keyword to the relevant code. So let's wrap our multiplication integer operation using the checked keyword like this. And now when we force an overflow exception to occur, the desired exception is thrown. We will now be able to handle the overflow exception as per our requirement. So let's also wrap the other integer operations using the checked keyword. So the next obvious question is, how can we handle exceptions in C#? Well, the C# language provides us with the ability to create try-catch blocks. So let's write the basic structure for a try-catch block. So the try section of the try-catch block code is denoted by the try keyword, and we must include the code on which we want exception checking to be performed within curly brackets that follow the try keyword. Within a try-catch block, we can include 0 or more catch blocks. Each catch block denotes catching a particular type of exception. Optionally, the developer is able to include a finally block, which is denoted by the finally keyword. Code within the curly brackets, following the finally keyword, will be run regardless of whether an exception occurs or does not occur from code within the relevant try section. So the finally section is ideal for performing cleanup code, for example, closing a file or a database connection or disposing of objects. If, for example, a line of code that writes text to a particular file causes an exception to occur, without the finally block including a line of code to close the file might be left open, which could result in undesirable consequences. Okay, let's cut our code and place it within the try section of the try-catch block. As discussed, all exception types in C# inherit from the exception class. So the exception class is the base class for all exception types in C#. So if we implement a catch statement like this, where we have a catch block to catch exceptions of type exception, we are literally implementing code to catch all exception types, because the exception class in C# is the base class for all C# exceptions. So let's test this. Let's force an exception of the type format exception to occur by doing what we did earlier, i.e. pressing enter at the prompt for the first operand value without entering any data. The difference this time is the exception is no longer unhandled. We are catching the exception in code through the use of our newly implemented try-catch block. The format exception class inherits from the exception class, therefore the format exception class is of type exception. The format exception class is more specific to the nature of the exception that we are forcing here, but because the format exception class is of type exception, the exception will be caught in the catch statement that is coded to catch an exception of the type exception. So let's test the code. And the format exception is caught as expected. The message states input string was not in the correct format, which is an expected outcome. So let's run the code again. Let's enter the first operand as a valid integer. Let's enter the second operand as a valid integer, but with a value of 0. And then to force our next exception, let's enter the / operator symbol, which represents the divide operation. And when the operation is executed, the error is handled, but the exception that is caught is not the most derived exception. What does this mean? The most derived exception class appropriate to the exception that has just been thrown is the divide by 0 exception class. Okay, so now if we force an overflow exception, code within the same catch block is run. It is not recommended to handle multiple types of exceptions generically like this. It is recommended that the developer should always use an exception type that most reflects the nature of the exception being caught. And if we force another overflow exception, but this time the overflow exception is caused by the result of the integer operation falling outside the range of values supported for the integer data type, this is also caught in the catch block denoted by the exception class. The problem here is that we are generically handling all the exceptions in this catch block. the developer can make provisions in code to handle each relevant exception type individually. This builds robustness into the code and also greater intelligence into the code. We can then specifically track each exception type and handle each specific exception type appropriately and not be restricted to one catch-all block of code for exception handling. So to enhance clarity regarding the different sections of the try-catch block, I'm going to format the output from the catch block so that the text stands out. So here I'm going to change the background color to white and the text to red. I'll also output text specific to the finally block and text specific to the beginning of the try block. So if we change our catch block in code to catch exceptions for the arithmetic exception type, let's see what happens when we force one of the operands to overflow. The error is caught and handled, but the class used to catch the exception is not the most derived class for the overflow exception. The overflow exception type is the most derived class that reflects the nature of an overflow exception. And although the arithmetic exception type is more specific than the exception type in terms of the nature of the overflow exception, we are now not handling all the exceptions that can possibly occur from the code within the try block. Let's prove this by forcing a format exception to occur. We can do this by simply leaving an operand field blank and then pressing the Enter key. And now you can see that we are handling arithmetic-specific exceptions by implementing code to catch exceptions of the type arithmetic exception. But we are not handling exceptions of the format exception type, for example. Previously, when we were generically handling all exceptions by implementing a catch block for the exception type, the format exception, as well as any other type of exceptions, would have been caught in the exception catch block. So to address this issue, we can include another catch type filter for the purpose of catching format exceptions in our try-catch block like this. If we now force a format exception to occur, this time by entering alpha characters into one of the operand fields, as you can see, we are now handling format exceptions. So let's force another arithmetic exception to occur. But this time, instead of an overflow exception, let's force a divide by zero exception to occur. And you can see that this exception is being handled within the catch block denoted by the arithmetic exception class. So let's look at the inheritance hierarchy, of which the arithmetic exception class is a member. And if we right-click the arithmetic exception name in our code editor, then click the context menu item marked Go to Definition, we can see that the arithmetic exception class inherits from the system exception class, and if we repeat the last action on the system exception class, you can see that the system exception class inherits from the exception class. You can see that the arithmetic exception class is part of an inheritance hierarchy. The arithmetic exception class is more derived than the system exception class and the exception class. We can, for example, catch the divide by zero exception by implementing code to catch an arithmetic exception, because the divide by zero exception class inherits from the arithmetic exception class. But the arithmetic exception class is not the most derived class that most reflects the nature of the divide by zero exception type. We should catch a divide by zero exception by implementing a catch block that specifically catches a divide by zero exception like this. And the same applies to the overflow exception. An overflow exception can be caught by implementing code that catches the arithmetic exception type, but the arithmetic exception type does not only catch overflow exceptions, it can, for example, be used to catch divide by zero exceptions. So the arithmetic exception class is not specific enough in the inheritance hierarchy for our purposes. We need to use the more derived class for an overflow exception, i.e. the overflow exception class. So if we right-click on the overflow exception class name in our code editor, then click the Go to Definition context menu item, we can see that the overflow exception class inherits from the arithmetic exception class, and we can repeat this until we get to the exception base class. And we can prove the same is true for the divide by zero exception class. Let's run the code again. And now if we force an overflow exception to occur, but this time not because one of the operands is too large for the integer data type to handle, but because the result of the multiplication operation is too large for the integer data type to handle. You can see that the message written to the screen by code within the overflow exception catch block does not describe the nature of the exception. It does accurately describe the nature of an exception that occurs when a user enters an operand value that is too great or too small for the integer data type to handle, but the overflow exception is not being handled appropriately for when the result of an exception operation causes an overflow exception to occur. So the question is, we have reached the most derived class to handle overflow exceptions. So how do we resolve this ambiguity, i.e., of when an overflow exception is caused by invalid user input, and when the overflow exception is caused due to the result of a mathematical operation being too large or too small for the integer data type to handle? The solution to this is to implement a custom exception. I hope you have enjoyed the second part of this tutorial on exception handling. In the third part of this tutorial, we'll create a custom exception class and appropriately integrate it into our application. Please like, subscribe, share, and comment. It will be greatly appreciated. And please ring the bell so that you can be notified of future content, which will be coming soon. As always, the code in this tutorial can be downloaded from GitHub. Please see a link which can be found below in the description to the appropriate GitHub repository. Thank you and take care.